Hello. In this lesson, I'm going to solve an example where I'm going to use equation of motion for rigid bodies in planar motion to find acceleration of the center of mass of this disc-like structure for two cases. All right. Let me first explain what we have here. We have this satellite, so it's a disc-like structure because it looks like disc. We have this satellite with 4 rockets around the satellite, A, B, C, and D. So what we are interested in is to find the acceleration of this satellite, both translational and rotational acceleration, for two cases. One, A, when all the rockets fire, meaning that A, B, C, and D are all turned on, and when all but D fire, meaning that when A, B, and C fire, but D does not. So for both cases, we're going to use equation of motion for rigid bodies. So we said that, again, this is a planar motion. The satellite is located in IK plane or XZ plane, and it's going to stay in this plane. So we're going to assume that we have a planar motion. The weight of this satellite is 250 pounds. The radius of gyration is 24 inches. The radius is 32 inches. And each of these thrust forces, when they are on, when they fire, is 4 pounds. 4 pounds force. We have T, 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 and T. Let me also add this T here. Alright. Let's see, part A. What happens when all the rockets fire? When all the rockets fire, you can just look at the physics and understand that because of the symmetry of the points where the forces, thrust forces are applied, the sum of forces is going to be equal to 0 along x-axis and z-axis. So for part A, sigma fx is 0. Therefore, m r double dot x is equal to 0. So I'm using r double dot to describe the acceleration. If it is easier, I think it might be easier if I replace this with just x and say mx double dot is equal to 0. So if I just replace, I'm gonna clean this. And I'm going to use x, y, and z to describe translational acceleration, translational position, and then translational acceleration of center of mass. And also, sigma f z is going to be equal to 0, meaning that m z double dot is also equal to 0. So from these two equations, we see that x double dot is equal to 0, z double dot is equal to 0. So the translational acceleration of point of the center of mass is equal to 0 because in part A, all rockets fire, meaning that if you look at the sum of forces, A points in negative I x direction, and at C, the force points in positive x direction. So the sum of forces is going to be 0 along x direction. Same thing along z direction. The sum of this force, which points in negative z direction, plus this force, which points in positive z direction, is going to be equal to 0. Alright, so we have realized, or we have shown that the translational acceleration in x and z direction are going to be equal to 0. Now, question is, what happens to rotational acceleration? Again, rotational acceleration is omega dot. So if in planar motion, we said that the equation of motion, rotational equation of motion simplifies to, in this case, rotation, possible rotation, occurs about y-axis. So we are in xz plane, therefore we have my equal to iyy omega dot about y Alright, so to compute this omega dot, which is angular acceleration about y, we are missing some of moments and mass moment of inertia about y-axis. So how do we compute the moments? We are interested in rotation about the center of mass. We have all the forces. Moment is simply force multiplying by moment r. In this case, that's equal to the radius of this satellite. So, moment, sum of moment is going to be minus 4rt. Each force creates a moment as big as RT. And in terms of direction, if you look at this coordinate system, X and Z, your positive y-axis points out of the page. But these forces create a moment about negative y-axis. So your moments have a negative sign. And then next we're missing mass moment of inertia. How do we compute mass moment of inertia? Let's say we don't have access to tables. End of any textbook, there is a table where you can see the definition of mass moment of inertia and how you would compute that for common geometries. Let's say we do not have access to that. Here we are given the radius of gyration and we are given weight. We said that once we have radius of gyration and mass, we can square radius of gyration and multiply mass by mass to compute mass moment of inertia. So, I'm going to do that. So I'm going to replace this Iyy with ky squared m omega dot y. Now, where do we get mass? We have the weight of this object, so we simply can compute mass from that. So we get minus 4. The radius was 2.66 feet. The force was 4 pounds. And that's equal to Ky was 24 inches. And I'm going to change the unit, all right? 250 over 32.2. And then this unit is slog inches squared. Let's keep the units. Omega y. So if you do the conversion and replace inches squared with feet squared, right? In other words, if you divide your inches by 12, you get in feet. What you're going to have is, so let me just write down the final number. So you get minus 16, 2.66 being equal to, I have 31.056 multiplying omega dot y. And this is in a slog, feet squared. And from that, I compute omega dot y being equal to negative 1.3739 per second squared. So once we have all the numbers or all the input variables, it's pretty straightforward to compute acceleration, the translational acceleration and rotational acceleration of center of mass. Now let's look at part B. So let's look at the physics again. So in part B, what we are saying here is, what if A, B, and C fire the rockets for this satellite? A, B, and C fire, but D does not. What happens? Alright, so let's start with translational equation of motion. Sigma Fx is equal to what? So again, A, B, and C are on. So if we sum all the forces along x direction, what we have here is B and D were along z direction. They do not affect the sum of forces along x direction. So this force again cancels out this force, and we get sigma Fx equal to 0. So we have mx double dot again equal to 0. So from this, we can say that x double dot is equal to 0. Just one thing here. Note that I have just dropped the subscript g, meaning that these numbers, x double dot and z double dot, are for center of mass. So let me ask you again, how about angular acceleration? We said that for rigid bodies, angular acceleration and angular velocities are the same throughout the body. So we do not specify the points because it's the same for all the points. However, for translational acceleration, we need to identify points. It is true that if you have a pure translation, the translational acceleration is going to be the same for all the points. But we always identify the points because when we have both rotation and translation, the translational acceleration needs to be defined for a certain point. Because then we are defining the rotation about that point. Okay? We define it about that point, but if somebody asks, what's the angular acceleration for this body, we're going to just give them one number. Sigma fx is mx double dot equal to x double dot equal to zeros. Therefore, translational acceleration along x direction is equal to 0. Now let's look at translational acceleration along z-axis. How about that? We have this force at B pointing in negative z direction, and at D we are not anymore applying any force. Therefore, the sum of forces is going to be negative t, and this is going to be m equal to mz double dot. So from this, z double dot is equal to minus 4 over mass. Alright, so let me compute mass here, make it easy. 250 pounds over 32.2, it gives me 7.764. All right, it's logs. So minus 4 over 7.764, this gives me 0.5 feet per second squared. And then we have rotation, just like before. So again, let me also compute I by y here. Again, ky squared m, and this is 31.056 slog per feet squared. Sorry, slog feet squared, not per feet squared. So rotation. So we have I by y, just like what we had for part A. All right. So now what is the difference between part A and part B when we are deriving or we are solving the rotational equation of motion? So we said that I by y, as long as we computed with respect to the same frame, for the same body with the same mass distribution, it's going to stay unchanged. Right? So that doesn't change. Part A and part B, it's going to be the same. However, because we don't have forces applied to the point D, this point, the sum of moments is not going to be any more the same. Instead of negative 4 RT, we are going to have negative 3 RT, right? All right. The rest is going to be the same. Then we solve omega dot y. We have same radius, same force, 4 pounds. We solve for omega dot y, and our omega dot y for part B is going to be negative 1.03 per second squared. So to summarize, we have used translational and rotational equation of motion, and we found translational and rotational acceleration for this satellite as it does a planar motion. So when it experiences a planar motion, for two cases, one case we had 4 forces applied to the circumference of the satellite, and for the second case we have 3 forces, right? Thanks for paying attention.